So I guess we can start. Welcome everybody to this session of the Newton 1665 seminars. We're going to have two talks on similar but different topics. The first one is going to be by Miguel Escudero, and he's going to discuss about the Euclidean wormholes and the recent results that they had on these. So Miguel, please, if you can share your screen. And the floor is yours. So please, whenever you want.
Awesome. So first of all, thank you for the invitation. It's really a pleasure to be talking about wormholes. And also, first of all, thanks to my collaborator, James Alby, for the hard work and key ideas that led to the paper that led to the invitation. So I'm going to talk about Euclidean wormholes and what their potential implications for the action quality problem. And let me start with some introduction. So we approximate and exact global symmetries widely in particle physics. We use them to maybe stabilize dark matter, to understand the lightness of a potential scalar field doing the role of dark energy in flavor physics, and we have them in the standard model. And in particular, the Peccei-Quinn solution to the Strominger problem relies on a new global chiral and anomalous U1 Peccei-Quinn symmetry. So that's on one side, we use these symmetries, and on the other side, there is this expectation that global symmetries are expected to be explicitly broken by gravity. So this typically goes by black hole arguments. Then specific examples include the string theory. It's really impossible to make a global symmetry in string theory, and there are no global symmetries either in holography. The question here is by how much? And in this context, wormholes allow modulo some caveats that I will discuss later to potentially estimate these effects of global symmetry breaking. So what are wormholes? In this talk, I'm going to consider wormholes that are gravitational instantons that contribute non-perturbatively to processes that violate global symmetries. So this is more or less the picture of the wormhole that I have in mind for this talk. And essentially, the wormhole that I'm going to discuss are microscopic and have sizes similar to the Planck scale. Since this wormhole lives at the Planck scale, we can integrate them out, and the low energy observer will see their effect as a tower of effective operators, like this one, that explicitly break the global symmetry. Again, here consider a scalar field with a U1 symmetry, and that has a potential like this form. So we have first an alpha parameter, which is a parameter that is determined by the vacuum state of the wormhole system, which we don't know, we don't have access to this. And then the entire operator is proportional to e to the minus the action, because this is a non-perturbative object. So a lot of the talk is going to be about what are the values of the action such that we know more or less what is the effect on the effective operator. So the plan for the talk is to see how gravity meets global symmetries, and in particular in the context of Euclidean wormholes and the QCD axis. So the outline of the goal of the talk is the following. First, I'm going to discuss what is the action quality problem, and then I'm going to get into the details of how Euclidean wormholes can break global symmetries, and in particular, I will discuss the Wormhole Dynamics and how the action scales in different theories and models, which I think is what the organizers are particularly interested in. And then I will discuss implications for action model building and some caveats, there are several, and then just mention some words for outlook and summary and conclusions. So please, in this part, this is going to be a short introduction. In this part, feel free to stop me and ask me questions if there are. Cool. So what is the storm CP problem? So this is the Lagrange that parameterizes CP violation in QCD, and is parameterized by this effective angle that is a mixture between the topological vacuum suspressibility and the argument of the determinant of the quark mass matrix. And observationally, we know that the angle must be below 10 to the minus 10 due to the non-observation of a neutron electric dipole moment. And this is the storm CP problem. Why this angle should be less than 10 to the minus 10? There have been an array of proposed solutions. The first one, which I think is the most compelling and is very interesting, and it leads to the title of the talk, is by Peccei and Quinn, which consists on introducing a new chiral symmetry, and I will discuss it in detail in what follows. But there are others. for example, one could imagine CP is actually a good symmetry of your Lagrangian and it's only spontaneously broken by the vacuum. And then maybe the argument of the determinant of the Gubar mass matrix is very small. This is technically natural, although it's not free from issues, but it's interesting and a viable possibility. One may think that maybe the up quark mass is 0, that will solve it, but this is highly disfavored by lattice calculations. One may think that this is not a problem. That's interesting too. And also, some people have highlighted that maybe there is actually no problem. So all of them, I think they are interesting. I'm not going to discuss them, and I'm going to focus on this one, which I think is by far the most popular one. So the idea of the Pechi-Quinn mechanism is to dynamically relax theta bar to 0. So in order to do that, Pechi and Quinn introduce a new global symmetry that is chiral and is a U1, and we call it U1 Pechi-Quinn. And then, of course, you need to introduce a scalar field, phi, charged under this symmetry. And the angular component of the field is the action. So the relevant Lagrangian in the Pechi-Quinn scenario is this one. So we have a term now, since this is a chiral symmetry, then the action couples to GG dual. Sorry. Yeah. And the Pechi-Quinn symmetry is actually not a very good symmetry because it's actually explicitly broken by QCD, and QCD instantons generate a potential for the action that looks like this. So this is a potential for the action, and then you need to minimize it to find the vacuum. And what you find is that then the action takes a vacuum expectation value. And if you compare the vacuum expectation value that you take to this term, you see that the Stone CP problem is solved because there is no CP violation in the vacuum. In addition, since we have a global symmetry that was broken, a Colson boson is generated, but since it's explicitly broken, the symmetry by QCD instantons, it's a pseudo-Goldstone boson with a very small mass, and this is the axion. Very interestingly, the axion can be a dark matter candidate, and the typical benchmark numbers for that is if the axion has 10 microelectron volts of mass with a scale of symmetry breaking at 10 to the 12 GeVs if the Pechi-Quinn symmetry was broken after inflation. Although these can be different, but this is, let's say, the benchmark that I will be using. So what is the action quality problem? Well, the action quality problem is that the Pechi-Quinn solution is strongly sensitive to the explicit breaking of this U1 Pechi-Quinn symmetry. So to see that explicitly, let me show you the action potential as generated by QCD instanton. So it's this red curve, and then if you minimize it, you end up here, which is CP conserving vacuum. So you solve the Stone CP problem. However, when you include any additional contribution, let's say this blue one, then you need to sum the two sources of the potential, and this is the total action potential. And when you minimize it, then you see that you end up in a CP violating vacuum. So in order for that not to happen, you require the additional contributions to the potential to be 10 to the minus 10 times smaller than the QCD barrier. That until now doesn't mean anything, but then we can try to understand what that means in terms of an effectivity theory. To highlight the point, let's consider a dimension 5 Planck suppress operator that breaks the Pechi-Quinn symmetry by 1 unit. So then this needs to be smaller than lambda QCD, roughly. And that means that the dimensionless coupling in front of the operator needs to be 10 to the minus 40 for a Pechi-Quinn symmetry breaking a scale of 10 to the 12 GeVs in order not to spoil the Pechi-Quinn solution to the Stone CP problem. And this is what goes in the literature by the action quality problem. So there are 3 ways out. One is, well, you may protect the action with gauge symmetries and forbid operators that are dangerous. So let's say you imagine you have this type of operator, they are of dimension D and break the global symmetry by n units. Then if you stick to the benchmark numbers and you assume that the coefficient in front of the operator is order 1, the dimensionality of the operator should be larger than 11 and 12, or 12, more or less. And there is intensive model building in this direction, because if you protect the action by gauge symmetries, these operators just cannot appear. But importantly, prototypical axion models do not feature gauge protected axioms. So there is a gauge singlet scalar and therefore are not protected by gauge symmetries. Another possibility is maybe these dimensionless coupling constant are order 1, but the phases are aligned with the QCD instanton. That is possible, but will be extremely highly tuned. And in addition, the axion will be ultra heavy, which will lead to important cosmological consequences. So this is highly unlikely. And then the third possibility, which is the one I'm going to discuss in the context of wormholes, maybe these additional contributions to the potentials are only non-perturbatively and exponentially small, because they come from non-perturbative processes, and then the couplings are e to the minus s being the action of the non-perturbative object contributing to these processes. So if the action is larger than 190, then there is no quality problem. Before I go into wormholes, I would like to highlight that this is relevant to any pseudo-Goldstone boson. If you want to have light scalar fields at dark energy, they may face the type of problems. We sometimes want light scalars to behave as dark matter, same thing. There are light scalars potentially related to neutrinos in the dark sector or in string theory. And those could all potentially suffer from the same problems. So let's now move into the gravity bit of the talk, and in particular into wormholes. So wormholes, in principle, modulo some caveats that I will discuss, allow for a quantitative assessment of the issue. So I'm going to discuss some Euclidean wormhole basics, and I refer to the nice review by Arthur and collaborators, and by Alonso and Urbano, a recent paper not substantially more recent than the pioneering references. But essentially, the key points of Euclidean wormholes is that they represent saddle points in the Euclidean path integral. And as such, they mediate topology change transition. So this is our Euclidean flat spacetime. And a wormhole will change the topology from flat spacetime to a topology with a flat spacetime plus a baby universe, so a 3-sphere in this case. So these wormholes, in particular, are supported because a given amount of global charge flows through the throat. And as I said, they have close to Planck sizes, and their effect to the lower energy observer has the explicit breaking of global symmetries. So they generate a potential of this form again. So we have these alpha parameters that we don't have access to. And then you have a tower of effective operators that are modulated by couplings that are proportional to E minus the action of the wormhole. If you go to the lowest possible operator with n equal 1, then you see that actually this contribution to the potential is not actually Planck suppressed, but is Planck enhanced. It goes like this. And if you don't want this to spoil the efficiency of the Pechi-Quinn mechanism, the action again needs to be 190. So now I'm going to discuss details about wormholes, and let me be specific about what do I mean by a wormhole. So actually what I mean by a wormhole is half a wormhole, and it has a metric like this in Euclidean spacetime. So it's a closed FRW metric. It goes like this, and here R is just the scale factor. So this is the picture that I show for the wormhole, and this is how R looks like in a generic example, and you can see the two regimes. So here on the x-axis is Euclidean time, and here on the y-axis is the scale factor. So this region corresponds to the throat of the wormhole that has a given size, close to the Planck scale in this case, and then you have Euclidean flat spacetime. So the key quantity here is the action, because it's going to tell us the probability of nucleation of a baby universe or the transition between various topologies, and can be written in more or less full generality like this. So first we have the Einstein-Hilbert action, then we have an action for the matter content that will be different depending upon your scenario. Then, since these things have sizes of the Planck mass, you may expect additional gravitational corrections, and then you have surface terms in order to have a well-defined variational principle. If we look at these, then a leading approximation, we can clearly see the following. So just by dimensional analysis, this gravitational term is going to be the Planck mass squared times the size of the wormhole. So that's the first term. Then we have terms containing the matter, which will be extra contributions to the action coming from dynamics. And then we have surface terms that are leading approximations we can typically neglect. So to have an idea of what are the typical actions you find, let me do a short timeline in 4D. Let's just stick with 4D. So here are the scenarios, the action scaling, and whether there is or not a quality problem for, let's say, benchmark numbers. So the first wormhole ever to be found was actually by Giddings and Strominger in 1988. And they considered the case of an action minimally coupled to gravity. And then they found that the scaling of the action is like this one. So n plan divided by fa. And if you take fa 10 to the 12 GeVs, there is no quality problem for the action. Then in the very same paper, actually, Giddings and Strominger found the solution, including the dilaton in 4D. And they found you can find an action that scales like this. So it's the same linear scaling modulated by the string coupling strength, no quality problem. And then Abbott and Weiss and Coleman and Lee studied the case of an unbroken U1 symmetry within general relativity. And what they actually found is that the action diverges, so it's infinity. But they argue, and if you take it to infinity, then you should not find any effect from these wormholes. But they argue that that's an artifact from the infrared, and that in fact the action should look like log of n Planck divided by the mass of the charged scalar field under the U1 symmetry. And if you plug in representative numbers, then this leads to a large, and not too large value of the action is only logarithmically dependent. Yep. In the same paper, Abbott and Weiss, and later in more detail, Carlos, Linde, and Saskin studied the case that is more interesting because it corresponds to typical action models of spontaneous symmetry breaking U1 symmetry within GR. And what they found is a similar logarithmic scaling that is unplanned by FA. And again, you take typical numbers and you find that there is a quality problem. In that paper, Carlos and collaborators studied this spontaneous symmetry breaking case within many setups, considering a wide variety of potentials for the radial mode, and they found that the action still scales like that. And our very modest addition to the list is that we consider this spontaneous symmetry breaking case in the presence of a dilaton in a very simple open string limit, for the limit of an open string. And we found that we still find the logarithmic term modulated by the coupling strength. And unless this coupling is below 0.1, which is different from the 0.7 one may expect from gauge coupling modification, there is a quality problem. So in order to understand the scaling of the actions, let's have a look at each of the cases. So this is the action describing the Giddings and Strominger wormhole. And you can see from the action that it's just the theory of Einstein gravity plus the action. So theta is the action divided by FA. So it's the action. The axion, sorry, not the action. And FA is just the axion decay constant that parameterizes the interaction. This is a surface term. So charge conservation, because there is an amount of global charge flowing through the wormhole, imposes this constraint. And then if you work out the equations of motion, they look like this, with L being roughly the size of the wormhole. That scales like 1 divided by the square root of n Planck divided by Fn. If taking the previous ansatz for the action is just n Planck squared times the size of the wormhole square, then you find that the action is n Planck divided by Fa, and you can find this actually analytically. So this is more or less how pictorially the wormhole of Giddings and Strominger would look like. You have a scale here, and if you lower it from here to there, then you see that the wormhole gets larger and larger. So that's qualitatively what happens. And the interpretation is simply that the flow of global charge requires the wormhole to be larger if you reduce Fa. And since you are making the wormhole larger, it generates a larger action because now the surface of the throat is larger. So that's the interpretation. let's now go into the case, which I think is most relevant because typical Axion models feature this scenario in which you have a U1 symmetry. So you have a radial and an angular mode. The angular mode is the action and the radial mode is just a scalar field that is spontaneously broken. So this is the theory. Here, this is gravity. We have the radial mode, and then we have the axiom, and a potential for the radial mode. At this point, there is, of course, no global symmetry breaking. And this is the potential. So this is the standard spontaneous symmetry breaking potential for a scalar field. You can do the same game. Charge is conserved flowing through the wormhole, and this is the equation of conservation. You can derive the equations of motion, nothing particularly interesting there. And then at R0, you need to have a good regularity conditions, which means that the R prime at 0 and F prime at 0 should be 0. And then when you go into the equations of motion, that really tells you roughly that F, the radial mode at 0 Euclidean time, should be roughly the Planck mass, and the size of the wormhole is roughly 1 divided by the Planck mass. So that's a generic result that you get from the equations of motion, and this is confirmed numerically. And then you go into your equation for the action, and you find that is m Planck squared times the size of the wormhole. You take these values, the size of the wormhole is just 1 divided by m Planck, and you get an action that is order 1. So this pictorially is what happens in this type of wormhole. So let's say you change FA from 10 to the 16 GeVs to 100 GeVs, and essentially you are seeing the same thing. The dynamic, the size of the wormhole didn't change, is roughly 1 divided by m Planck. So, and I think one of the key results of Kalos and collaborators here is that when you allow the radial field to vary, it is really difficult, it's virtually impossible to make the wormhole larger than 1 divided by m Planck. And therefore, the action is order 1 plus extra factors. And they show that this holds even if you modify gravity at very small scales and with very exotic and I would say extreme potential. So I think this is a generic result. So let's have a close look at the solutions in order to understand what is the actual, why each scaling appears. So this is how the radial mode profile looks like as a function of Euclidean time. And in red, I highlight the case in which the radial mode is dynamical, and in blue, the case in which the radial mode is non-dynamical. Of course, it's non-dynamical, it's just flat. And in the case in which it's dynamical, the saddle point is this one. And as I said, it takes values close to the Planck scale, and this is just an example. This is how the scale factor looks like, R of R. And then here you can see that indeed the Giddings and Strominger wormhole is substantially larger. But qualitatively, you see as more or less similar behavior of R. Of course, at large Euclidean time, this just goes to Euclid flat spacetime. So where is the log coming from? So in order to highlight that clearly, here I plotted the contribution to the action as a function of d log of R. So I put d log so that we can literally sum in this axis. So the action is going to be the sum done in the plot. And this is what happens in the case of the Giddings and Strominger wormholes, with the radial mode just being fixed to FA. And this is what happens when you have a radial mode that is dynamical. So you find a logarithmic scaling here, and this highlights that the action gets most of the contributions from the fact that it's larger, and therefore that's why you have a linear scaling. So in order to understand better this log scaling, we can go deeper into the action. So this is how the action looks like. So we have here a term that depends upon the derivatives of the radial mode, and then another one that is just pure gravity. So yeah, this is just the scale factor. Outside the wormhole, which in the radial, in this red case corresponds to scales that are in this area, R is simply a small r, is simply a square, the Euclidean time, and you can actually solve for this profile analytically. We do this numerically, but this is a good approximation. And then you can just take this formula for the action and calculate it. If you calculate it, you put f prime here, so it's something divided by r cubed divided by r squared, and then you get a log. So this is what you find, and this is what we find. So the action is 1 plus logarithmic corrections coming from the presence of this radial mode. So to summarize, in the Giddings and Strominger wormhole, the action goes like n plan by fa, and this is because the size scales like 1 divided square root of n plan fa. Including the dynamics of the radial mode makes the wormhole of Planck size, and then the action is order 1 plus corrections. And these corrections that are logarithmic are due to the fact that this is the work that it takes a radial mode to go to a Planck scale to fa as required by the topological condition. So you need to have that because you want to go to the vacuum in Euclidean space-time. So since typical Axion models do feature a radial mode, that means we should stick to this formula for the action. And therefore, you can compute the log, and this is shown in the plot. So this is the action as a function of fa, and you see that this is far from 100. Yeah?
Can you go back to the previous slide?
Of course.
Thank you. Sorry. Very nice talk so far. The logarithmic scaling is a little bit strange to me, in the sense of, like, if you think of in string theory, you can realize kind of microscopic versions of these wormholes as instantons. So Euclidean instantons, and then in that case, the decay constant is dynamical. It's a field. Okay. Like, for example, it sits in the same, if you have n equals 1 supersymmetry, it sits in the same multiplet as the axion.
Right.
And in that case, it has to be linear in F, because if it contributes to the superpotential, it's a holomorphic function of the superfield. So it's always like F is like 1 over the superpartner of the axion.
Mm-hmm.
So like if you call the dilaton the superpartner, let's say you think of the axiodilaton, it's like the superpartner of the axion. That also controls the decay constant, okay, and 1 over F. So the action if it contributes to the superpotential, all the instantons that I know of, it's always the case that the action looks like m Planck over F plus, so exponential F plus axion. And that just has to be the case from supersymmetry. There's no way that an instanton contributes to superpotential.
I'm going to discuss the case with the radial mode and a very simple, let's say, dilaton, which, so you mean this, right? That in string theory, you get something like this.
No, F itself is a superfield. It's a dynamical field, and it sits in the same multiplet as the axion. So if you write the exponential as a holomorphic function, it always has to look like 1 over F plus the axion, as far as I know, in all the examples that I know of. And I don't see how one can ever avoid. Do you know what I mean? Or if you don't know, then maybe
not really. Maybe we can discuss it at the end, and it may very well be. So my knowledge of string theory is limited. So
no, it's just supersymmetry. But okay, it doesn't matter. So okay, if you didn't know what I mean, then okay, thank you. Sorry to bother you.
No, not a problem. But let's come back to that. Okay. Good. So in this example, in like GR plus this scalar field with a spontaneous symmetry breaking pattern, this is the action that you find. I show that analytically, and numerically you find this. There are no other solutions. And then if you stick to this value of the action, you find that the action is so small, and therefore actions appear to have a quality problem if these are the instanton that contributes. Yet, I think this is relevant for gauge-protected actions. So this is the same operators that I wrote down before at dimension D, so they can be highly suppressed by Planck scale interactions. And typically, one will assume that these couplings are order 1. And then if you do that, then the dimension of the operator that is allowed to break the symmetry without spoiling the Pechi-Quinn solution should be larger than 12. However, if the value of the action that you take is the one that I discussed before, then actually the dimension is 12 minus n, n being the number of units that this operator carries that break U1, the U1 symmetry. So in principle, even though this action is not too large, the dimensionality of the global operators will be lower than expected if you assume that these dimensionless couplings are order 1. So here we did a very simple extension of what we did of the, let's say, GR case, and we considered the low energy limit of an open string theory, including the dilaton, in 4 dimensions. So this is the value that we found, 1 divided by GS, but the same log factor. And again, this is the value of the action as a function of the string coupling constant. And unless the string coupling constant is below, let's say, 0.1, the action is not large enough. So you do still have a quality problem unless this happens, which appears to be far from what you may expect from gauge coupling unification. What happens if you add further particle content? Here we did something very simple, so consider 2 U1 cases. And then we found a value of the action that is just the sum of 2 logs, nothing super exciting there, but one needed to check. And what we did find, so these are typical profiles in this scenario, what we did find is that the action is largely independent on the interactions between the fields. So that wasn't trivial, but you start modifying the potential of these 2 fields and you stick to this. It's very hard to change the action. If this is the action that you get, then the 2 pseudo-Goldstone boson become super heavy and strongly mixed, and this is the mixing angle. And unless the scales of symmetry breaking for each sector are very different, then they are strongly mixed, which means that the U1 symmetry is not very well defined on the first place. So now let's go into the caveats. And one of the caveats may be that the scenarios we consider were very simplistic, and that could be. And one very important one is the stability. So the solutions we are finding are saddle points in the Euclidean action, but one needs to check against small perturbations of this solution to actually ensure that they are really saddle points and that then they contribute to the amplitudes changing, breaking global symmetries, or processes breaking global symmetries. So this has been studied in the literature, and in fact, not too long ago, the Giddings and Strominger wormhole was shown to be unstable. So there is an instability in this region, which means that there are regions with smaller actions, which means that maybe the Giddings and Strominger wormhole is not the one describing the amplitude for these changes in topology. However, so far, there is no study dealing with the stability when you consider the radial mode in the spontaneous symmetry breaking case. And this is something that we are actually studying to see whether one finds again a problem with the stability as in the Giddings and Strominger case. Of course, there are other caveats. So one of them is high energy. So we are using initial conditions at Euclidean time 0, which corresponds to energy infinity, and something can clearly break down there. And maybe the compactification changes the picture, or maybe, as Eran, I think, was highlighting, supersymmetry changes the form of your potentials. That can be very well. And then there is an issue on the interpretation of wormholes in terms of alpha parameters. So we have alpha parameters in terms of the operators. And there is progress on that side. So recent analysis suggests that the interpretation of Coleman and Giddings and Strominger holds within holography. That's quite interesting. Recent studies also suggest that wormholes actually can play an important role in quantum gravity. Maybe they are not the same wormholes we are considering. That can very well be. But if the interpretation is correct, then we are still left with alpha parameters in front of the operators generated by wormholes, and this clearly limits the predictability. So the action is not the only thing. It has been argued that maybe the dimensionality of the wormhole Hilbert space is 1, and that would be good because then there is just one state, and perhaps arguments could be made to shape the single wormhole state. Wormholes are not the end of the story, and this is a nice paper that is trying to address the amount of global symmetry breaking with black holes at finite temperatures, but still wormholes could be behind part of the story, and there are several recent papers dealing with breaking of global symmetries by Hawking, by black hole evaporation in quantum gravity, taking into account the effect of wormholes, and this is quite interesting. So, in summary, in our study, we extensively studied Euclidean wormhole solutions that feature a scalar sector featuring spontaneous symmetry breaking. One of the takeaway messages is that the dynamics of wormholes we consider appear to be broadly independent on the additional particle content and interactions in this setup. And the dynamics of the dilaton does not alter the logarithmic dependence on the action. It simply modulates it. So to conclude, the efficiency of the Pechi-Quinn solution is strongly dependent upon species sources of U1 symmetry breaking. That was well known. Wormholes represent a quote-unquote control, because there are many caveats, and I discussed some, system to investigate gravitational symmetry breaking. And within this setup and the, let's say, simple wormholes we consider, typical Axion models appear to have a quality problem with the non-perturbative Einstein gravity. Even though these wormholes do lead to a large breaking of global symmetries, their values of the action could nevertheless be relevant for model building of gauge-protected actions. And of course, these statements are based on wormholes, which are subject to several caveats, but caveats that may nevertheless be resolved soon. We don't know. So to motivate that, I put a plot of the citations of the pioneer Coleman paper, and you can see a spike. So there is a lot of interest in these wormholes, and maybe some of the caveats are resolved soon. So with this, I finish. Thank you very much for the invitation, and thank you very much for the attention. And yeah, time for questions and comments. Sorry if I went over time. Sorry.
Yeah, don't worry. Don't worry. It's just 5 minutes. So are there more questions?
Can I ask a question? I don't know.
Yeah, please.
Should we just speak up or?
Yeah, just please, Gia.
Hi, this is Gia. Let me show.
Hi.
Hi. Yeah, thanks for the talk. So the since you also, especially since you also consider this string theory case, or in general, even without string theory, we can introduce Axion as a bimu field, anti-symmetric field. In that case, it has gauge symmetry. And in that case, you can show that the only operator that you can write down compatible with gauge symmetry is the topological susceptibility of the gravitational vacuum. There's nothing else. So if wormholes generate a problem, they can only generate it through topological susceptibility. But then the thing is that that topological susceptibility can remove whenever you have chiral symmetry, which is anomalous under gravity. And in the standard model, Pechi-Quinn symmetry is not the only one that is anomalous with respect to gravity. Also, for example, you have a combination in which neutrinos participate. And since neutrinos are light, that's an experimental fact. Neutrinos are extremely light. The chiral symmetry of neutrino Lagrangian is very good. And so you can trivially remove this topological susceptibility away. So, I mean,
I wasn't aware, so you know, I'm aware of the fact that the action field can be seen as a threefold.
Right, and then it has gauge symmetry.
But you know, it's the very same. So the starting point will be that you start with no global symmetry, with a global symmetry, right?
Well, that's a dual language to that. That's a dual, in terms of low energy effective theory, that's a dual language. It's not fully equivalent, obviously, because it's only low energy, but you can, what I'm saying is that, especially if you are in string theory, from the very beginning, you can introduce Axion as a bimu field.
Yes.
Okay. Now, bimu field carries gauge symmetry. It's invariant of the gauge shift. So it's on its own now, the Axion symmetry is realized as gauge symmetry. And now you have an extremely powerful monitoring tool, which tells you what kind of operators can you generate to violate it. I mean, and you cannot violate it because it's gauge symmetry. The only thing you can do is to give mass to this bimu from gravitational effects. And there is a unique operator that's a topological susceptibility of gravitational vacuum It's RR dual correlator. That's the unique thing. So if wormholes generate any problem, it has to go through that correlator because there is nothing else you can write down.
I see.
But fortunately, the thing is that people are not aware of this, that the same correlator you can remove by chiral transformation of neutrinos. And neutrinos exist, that's an experimental fact, and they do carry chiral symmetry. So it looks like that
I see, but
really protect, it looks like that this chiral symmetry really protects Axion, especially in BMU version.
I see, but my question will be, let's say you start with something that is not a string theory. What happens then?
Well, it's the same thing. I mean, what I'm saying is that if we are working in low energy effective theory, we can always introduce Axion as BMU field. And but the advantage there is that it's explicitly gauge redundancy. It contains gauge redundancy, and that gauge redundancy, as usual, is a very powerful tool for monitoring what kind of operators could be there. And you can see that the unique operator that is dangerous is topological susceptibility of gravitational vacuum. Simply, there is no other gauge invariant operator that could give mass to screen this BMU. And so that's why it's a very powerful framework to think in that way. Yeah, so that's
I will check the reference. I wasn't aware of that.
But also the interesting thing would be to see, maybe, I don't know, maybe you can see with your techniques, because this topological susceptibility of gravitational vacuum, it's an open question. So we don't know if wormholes really generate it. So it could be that wormholes they don't even generate it, because that correlator, when you saturate it by wormholes, it should have this pole at 0, and we don't know if that's happening. I mean, I had some arguments that even if wormholes do not do it, then micro black holes most likely will do it. By the way, micro black holes you didn't discuss in this talk, but that's another source of contribution, right? So anyway, yeah, it's an interesting question to see if these wormholes saturate that correlator.
Yeah.
Okay, so more questions. We still have some time.
If I can have a brief question.
Yes, please go.
Hi. So your result rely on assuming a radial mode.
Yep.
And I mean, of course, the radial mode is not generic of the Petrel-Quinn mechanism. There can be no radial mode, or it could be light, or whatever. So I was wondering whether these conclusions were generic or they apply only.
You always have a radial mode. I mean, you have a U1 symmetry, and then you have a charge scalar field. There is always a radial mode. Now, what is the fate of that radial? Yeah.
Just I give you the example of the composite action where you have some strong dynamics. There's no radial mode associated.
So in those scenarios, I will put them within the gauge protected settings, I will say.
Well, not necessarily. I mean,
okay, yes. In composite actions, I agree.
I mean, I want to know if in a composite action there is the problem of the wormholes or not. If I don't do the gauge protection.
I don't know. I actually will need to think about it. But that's a good point. I don't know.
More questions?
Thanks.
I have one question.
Yeah, go, Alessandro.
So, if I understand correctly, somehow this radial mode gets a Planck VEV, so manages not to go into non-perturbative quantum gravity, and that's why the action becomes a further one. But then, should I expect that what you get is just a naive dimensional analysis, which indeed looks a bit like what you get because the action is log and the exponential of log is power?
Can you repeat again the statement?
So this radial mode now takes to go into non-perturbative gravity, no?
It goes to, this is a typical profile. It's not a Planck scale, but close to the Planck scale.
So I would naively guess that if gravity becomes non-perturbative, what you should get is just the naive dimension analysis. So all operators suppressed by the Planck scale. no, which indeed is somehow similar to what you get, no, because you have E2 minus, let me try to type, you have E2 minus n log f over m Planck, and this is power.
Yeah.
So somehow it looks like the theory wants to do something like this, but no, if I check now the detail in the power, doesn't do this, so I don't understand.
So I mean, I think these plots highlights where the action is coming from. So it's actually coming from outside the wormhole. So, you know, this additional contribution is not coming from inside the wormhole. The wormhole is here. This is Euclidean time. These are scales below the wormhole length. And this is outside. So you see that the action contribution is coming from the outside. And therefore, I associate it, I interpret this as, you know, the work that it takes the radial mode to go from close to the Planck scale to FA, whatever FA is. But this is action that is coming from outside the wormhole. I don't see there how gravity, actually you can ignore gravity in this regime. You are outside the wormhole, it looks like flat Euclidean spacetime, but nonetheless, you have a contribution to the action just coming from the fact that you want to move from a topology that has some initial conditions to another topology, and then you need to do some work on the field. So it's not in the, you know, if this behavior was seen here, I would agree, but I don't see how gravity is becoming non-perturbative in this regime because we are outside the wormhole. There are no strong, yeah, anything that happens below here, we really don't have control. But above there, you know, provided that that this is actually a solution, which no one knows, then the action is really coming from the outside, the wormhole.
Okay.
So in other words, if I understood correctly, this, so I think I agree with what Alessandro was asking, that once your solution goes into Planckian regime, Planckian regime, of course, we cannot trust it, and so this means that. But that's unfortunate. But that's the state of art. It's like we are always looking under the lamp. I understand, but what is important is that you have self-contained transition amplitudes. You can compute transition amplitude self-containedly, while entire solution stays outside of Planckian regime. Is that the case?
Well, I think this will, so if we have a look at the profile, this is how large it gets. So it doesn't go above Planckian, but it's close to be Planckian.
Well, it's pretty close. I would, if that's what you need all the time, then I would be worried.
No, man. I said it in the caveats. You know, we are in a region that.
No, of course, no. I understand. But what I'm saying is that, I mean, there's sort of three levels of problems. I mean, the first level is when we cannot avoid going into Planckian regime. In other words, whenever I have to compute amplitude, I have to hit the Planckian regime. That's unfortunate. There could have been a second level where at least there is subclass of amplitudes that I could evaluate without entering in the Planckian regime. And then I could hope that the other part is small or whatever. So that was the, So it's important which one is the case. So
I mean, if you look at the solutions, and the red one is the one to be looking at, you know, as soon as you go so this really gets Planckian really inside the wormhole, where you may say you have lost control of what happens, but outside it's up Planckian.
So that's so if you can consistently evaluate the amplitude while all the time being outside, then I would say it's okay, it's a legitimate.
Right, but so I mean, so the estimate is the following, you know, like just by dimensional analysis, the part of the action contributed must be m Planck squared times the size, and the size in this type of solutions is just 1 divided by L by m Planck. So it's order 1, and then you pick up a extra factor that is coming from the outside. So I think
small. Yes, I understand. So
it's something a logarithm that is small to something that is small. So the logarithm dominates. So
no, I understand. So I think that Alessandro's question was about this domain where Planckian Planckian domain, which you cannot control. And yeah, I think that's
correctly. I mean, the choice in this plot of f10 to 16 GeV is a bit unfortunate. If I understand correctly what you say, if you choose a smaller f, the action will be dominated by values which are much outside the wormhole.
Yes, so
this, go back to this, exactly.
This will go for longer and longer that way.
Longer and longer. So most of the logarithm will build up in a region which is much sub-Planckian.
Yes.
And at that point, okay, you know that the wormhole itself is small and would give you maybe a naive dimensional analysis contribution. But then you have a logarithm which is supported outside the wormhole, which gives the most of the action, let's say.
In this case, yes, but if the wormhole were to be larger than the Planck scale, substantially larger, then that term will dominate.
Yeah, I mean, unfortunately, the problem is upside down, right? In other words, the typical problems in this gravitational non-perturbative effects contributions, they come from the smallest size objects. So it's true, of course, it's the same is true about black holes, right? I mean, if I compute contribution of black holes to virtual black holes to topological susceptibility of the vacuum, the huge black holes, they are exponentially suppressed. I can forget about them. But unfortunately, we cannot control small black holes. And those are those that contribute most because they have the smallest action. So you are absolutely right that the contribution to the action mostly comes from the big objects because they have the largest action. But the problem here is the small action, not the large action. So yeah, you have to shield yourself somehow from the domain of small actions because they are the least suppressed ones. And but I think that's a state of art. I mean, I don't think until we can solve gravity at Planck scale, right at the Planck scale, this will remain this issue.
Yeah.
Okay, so Aaron, last question by Aaron, and then we move on.
It's a very quick comment. It's not a question. I think I understood why this inconsistency is happening. So can you write down? Can you show me the slide with the action that you're using to find a solution of it?
Yes.
Yeah. So here there's some kind of ambiguity here in this action because f is chosen in front of the Axion kinetic term, and then you've chosen to canonically normalize it in a kinetic term. Mm-hmm. But there is an arbitrary prefactor which can depend on f in front of that kinetic term that you've chosen to. In the kinetic term for f, the kinetic term for f is canonically normalized.
Yes.
Then you've also put f in front of the Axion decay constant, so that you cannot have complete degree. You cannot have complete freedom. You cannot choose to canonically normalize it and also have that f in front of the Axion. Or
no. But okay, one second.
Anyway, the point is that in string theory or in string theories that I understand, there is a factor of 1 over f squared in front of the kinetic term for f. So if you choose to normalize f so that it's f squared is what's in front of the Axion, then the kinetic term for f is not canonically normalized. You can canonically normalize it, but then it would be like log of the kinetically normalized field. And
that's the dilaton coupling, right?
Sorry?
If you have a dilaton coupling, right, then that happens. But this is not a dilaton. That's, this is just a free field.
In supersymmetric theories or in string theory, in any situation that I know of, it is like a dilaton. So it has a coupling like that. And that changes from linear to logarithmic behavior. And that's why it's happening in those theories. Now, I'm not saying this theory is not possible, but I'm just saying that in the theories that I know of, what you get is you get a 1 over f squared in front of the del f kinetic term. That changes this logarithmic to linear behavior. But that's just I think that's the concrete reason that you're finding these logarithms, but that's just a comment. Yeah.
Okay, I would suggest